representations. So now it's a little bit more abstract. So first we have like p-zp, psi module. So what is the p-zp psi module? So that means it's an OL module. You have p-zp action. You have psi action. And then you have some compatibility condition. What is this kind of compatibility? So you have psi, because psi is always commutes with gamma. So, but gamma, what is gamma here? So gamma is always this, right? It's Zp. So that's psi commutes with this. The second is psi. You know, psi phi A B is A psi B. Okay, so the same thing is here. So 0 PB 0 1 Z is 1B 0 1 Z. Okay. So that's kind of condition is from pi gamma module, but here we just for any, so it's just n. Now for this n, we have some examples. So there are many examples you can have. Say m is just d, the one we have here, or you just a d0, zp, or any a. A is, for example, is OL. L. Yeah. So the second one is we have this D plus, D natural, D sharp. All these are p-zp psi module. Then, if we have this module, the proposition is again we repeat the proposition there. So there exists P copy action and it's unique such that. So it's again satisfies the three conditions. So the first condition is if you have p to the k 0, 0, 1 x of n, you just get x of n plus k. The second one is you have a0, 0, 1. Okay, you get is a0, 0, 1 x of n, and it's contained in Z. The third one, well, if you write is 1b 0 1 is yn, then it's just repeat this, okay? So this yn is just 1 p and b 0 1 xn for n is bigger than if for this. So if you again you have this action. Now with this action we also have this kind of m box tensor delta p or qp. What is this? This is just if delta is a central character, is a character. Now here we already have BQP action. Now this is a B module. This is a B representation. So B is Borel. Okay. So PQP action is just there. But then what for the diagonal element? So for the diagonal element, so you just say if you have D 0, 0, D here, so you just act on by delta D, delta of D. Okay. Then you get, so because this B is AB 0D is Borel. So if you have parabolic one and you plot this action, you get a B representation. Okay, so that's the one you have. So the only thing missing is now the action of W is. Okay. So this is a PZP action. Now the second one is we call PZP, phi per psi module. So PZP phi per psi module is a PZP per psi module. And then you plus some other thing. So the one thing is some phi action, but the phi action you need some such that some kind of compatibility condition. So it's phi 0b is just 1 pb 01 phi. The second psi times 1b01 times phi is either 0 if b is in ZP cross, or is 1 if b in PZP. The third one is something like 0 to p minus 1, you have 1i01 phi per psi, 1 minus i01. This is just identity. Okay. So this for this I need to make a remark. So per psi, in the phi gamma module case, per psi is always P001. Okay? So if you take per psi in here, you can really find it. That's why 1 is true. So if we, in this PZP phi gamma module, we define this P001, this matrix, the action of this by phi. So this we will get P plus action. This we know is ZP minus 0, ZP on M. So for any M here, for a P, ZP phi per psi module M. Okay. So this one remark. The other remark is we have some examples of these. So D certainly, or D0 ZP. This is a PZP phi gamma 5% module, and also D dagger. This one is a PZP 5% module, but this and this No. Because you can see the phi action is not stable. Okay, so this is no. This is good. This is no. Okay. Now for this, the real thing is we need to define something of restriction. So we need to use the property here. So there's a number. Therefore, so for A is in ZP, K is in N. Let's say K A is just this. It's 1A01 phi K psi K and 1 minus A01. I don't know how he gets this, but anyway, you get this. So you have a number is this. You have 1 is this beta Ka. If you composite beta Kb, it's either 0 if A is not B modulo Pk. Otherwise, it's this. If A congruent to B modulo Pk. So the second one is you can add all this. I is 0 to P minus 1, K plus 1, A plus I Pk. You get this. You get this. So from this, you can see this is something like a restriction line. So we write this beta Ka. If you write down as this restriction, A plus P to the K, Zp. Now you can see this really satisfies the usual restriction condition. You have this this condition and this condition. You just check. Okay. So we need this. So for any m, we need this. Okay. So this is now for U. Compact open in Zp. You can define this U. So U is some disjoint union of J, and this Uj of the form A plus PKZP, right? So we define it's just this, the sum of okay. You will just define this. Now we have this. You can have something we had in the phi gamma module measure case is we can get psi is nothing but phi negative 1 times restriction PZP. This is really the one we have. We know phi psi is just restriction PZP. Psi phi is just identity. Okay, this is a one proposition. We have phi gamma module. So, but in this context, if we have this PZP phi gamma module, phi psi module, we also have this. And if M is just a measure case, then the restriction is the real restriction. It's the restriction we had before, or it's just a multiplication. Okay. So, and we also have the property of restriction. You can imagine All this should be true. So this is so this is should be true. What should be true is true. Okay. So this is a restriction map. Now, so this is for VP. What about for U is in QP? Is compact set in QP, compact open in QP. So we have, see, now first we look, M, we look, this is just the restriction map of M. For this one, we just let this. So U is ZP, you get, it's just M. And U is, you get 0. Okay, so that's the restriction map U. Now, M is contained. We know M is contained in M QP. So, how do we define this? We have an x here. We just define phi nx. Then we get a map from M to here. And this is a kind of injection. It's a map. Now, so now if U is compact open in ZP, again you can define this one. But how do we define this? This you can, because of this this map is contained in QP, right? So we just say this mu n, we use mu n or what? Xn. We goes to phi n and the restriction of this U x of 0. Then this map is okay. So this map, if U is compact open. Now if U is compact open in QP, then it's a little bit more. So if U compact open in QP, then what do we need? We just need, suppose p to the k times U is contained in ZP. Then we just define M is just p to the negative k, 0, 0, 1, M is just this, and then the restriction p to the k U. Okay, so that's the restriction. With this restriction, so we can get a map. So real map from here to here. Okay, then this restriction again satisfies the properties here. Yes, of course, yes. Okay. Yeah. And yes, you actually to prove this doesn't not depend on k, we need a little number I didn't write here. So it's this number, say the independence of k. Okay. We need to use this number. If G is in P plus and U compact open, in 0P, you can find the G restriction U is restriction GU in G. Because of this, you can check it's really independent. Yeah. Okay. Now we have this restriction. Then we can define MQPC. What is MQPC? It's just all this P minus KZP. Okay. So this one we can find it. It's just this. If you have all this xn, phi xn is xn plus 1 for n sufficiently large. So that's it. You know, if for n bigger than 0, this is true, then it's just n because of the definition. So here is just a for some n sufficient large, if this is always true, and then you have this with compact support. So this is the zeta element of M box QP with compact support. And then we also have another one is so-called MQPPC. This is only like it's just all this. And then you take the restriction of ZP 1B01 x is 0 as b goes to infinity. Approach to 0. So certainly you need here M must be topological. First we didn't say any topological structures. There. Okay. So this is plus infinity. So if b goes to plus infinity, this is 0. And you can check. This always contains this one. It always contains this one. Okay. So example. One example is M just B0 VP. And the U is open, compact in QP. And you can find, that's why we all have this kind of notation. This is just B0U. It's just the measures on U. Okay, so that's why you will always have QP and P. And this one, and this is just a real restriction. So if you have a measure here, you just restriction in QP, you get a restriction to U, and then you get this restriction. And this one is measures with compact support. So the set of measures. So with compact support. So this is the one we define this box structure in n box tensor product QP. There are lots of things, but one thing we need is this restriction. We need it, and also how to extend this. Now we'll move to the next section. So maybe it's 4.4. If we want to say it's just this. Okay. So delta, the delta structure is you just want to extend it for delta of n QP. This one, again, we need to first look about, let's take a look at the, so in this case, we just, W is just 0, 1, 1, 0, okay. Let's look at the continuous, and then delta is, so it's continuous. Unitary character. So first let's look about the measure case. We let pi delta is just all the functions from QP to L such that x goes to delta x and phi 1 over x is continuous at 0. So all these functions, continuous functions. So this one is a GL2 QP module. What is the actual GL2 QP? So if G x amp psi, or we can say G negative 1, what is this? ABCD x is just delta Cx plus D, and then for psi Ax plus B over Cx plus D. So ABCD is just contained in G, in this GL2 QP. Okay, so now let's look at the dual of this. There's mu, we call mu, is contained the dual of this. Just means is function, there is a distribution, or is a, suppose, now P1, what is P1? P1 QP is just say 2 copies of QP, of ZP. And then you glue in over ZP star. And then the gluing, inside the gluing you have this is just if the map is x goes to 0, 1, 1, 0, x, it's just this wx. Okay, so this you gluing over this line, and then you get a QP instead of yeah, this is P1 QP. How you get this? So good. So we can for mu in here. So we can let mu1 is defined by, so we can write down as this, but at this time you don't know what is this mean, because this is, so is defined by say Vp phi x mu is just this function, it's just this phi, it's just this mu, and then Vp psi, Vp phi. Because this is in the dual, so you have this parent, right? It's function, and then of its dual, you get a number. Okay. So you just define by this. So this looks like this. Okay. Now mu2, again we just say it's just Vp 1001 mu. So what is this? Vp, oh, this is mu1, phi x mu2. I just define as you have 0, 1, 1, 0 mu, because you have this action, Vp mu. You just define by this. So for this, now we just wrote this one. This is B0. We just, the notation is just this. Okay. Because this, I think this is contained in D0 Vp. Again, also this is also in D0 Vp. So we wrote down like this as mu1, mu2. So it's D0 Vp, D0 Vp. But because of this is green over there, so you will have, we need to have a condition is this restriction Gp star mu2 is the restriction Gp star mu1. Well, what is this? It's just defined by this. If you have a measure over Gp star, and then you just define this as delta x phi 1 over x and lambda. Okay. Then this one you get something. So this is like if we from this mu we get this mu1 mu2. So this is mu1 mu2, and because these are different copies, we want the identity. So we get this. But what is about this restriction of QP? Because we need this P1 QP certainly is including QP, right? Then this is, you have this mu is mu1 mu2. Okay, so you just think about this. You will go to some mu n, because so what is mu n? So we just say mu n. So x mu n. We just define as this map Pn 001 mu. then the restriction of this function at Zp. So this function, so because you see this function is in here, but because you can extend it, so it's really from P1 QP to L. So that's why you have P1 QP. So you have you make this P1 is 2 copies of Zp and green over Zp star, and then that's why you get this. Okay. So that's why we defined something called D0 Zp box state P1. Okay. So this is an example, and this is the first thing. Yeah, you always look at measures and distributions to find the correct formula. Otherwise, for the phi gamma module, it's hard to find it. So now for general, for D, what about for D? So D, again, so it's again about something we just defined, imitating this. It's contained in D times D. So you say this is Z, and the restriction of Zp cross Z2 is the restriction. It's just Z1. So this what is this W delta? So is what we have is given by a very complicated formula. Well, this formula is really come from there, but it's really hard to write. So it's actually this. N goes to plus infinity. I is in Zp cross modulo Pn. So you have delta I. You have minus I minus 2, I minus 1, 0, 1. You have this PMZP, and then you have 1 minus I, 0, 1, Z. And this limit exists. Okay, so this is really, really hard to find. And you can also, because of the relationship of restriction and all this, you can also write down the same thing. Looks a little bit neater. It's just this. I minus 2, I minus 1, or this 2. 0, I, and then you have restriction I plus Pn Zp. Take a Z. So this might be the nicer formula, and then you have a very ugly one. The ugly thing is, so here we use the action of G action, GL to QP action. But if you only use phi gamma action, then you have a very ugly one. So it's use I is Zp cross modulo Pn, and you have delta, and you have 1 plus I plus T to the I. So you just use the phi gamma module, and then gamma minus I to the square, and then you have phi to the n, psi to the n, and then 1 plus T minus I to the negative 1 Z. Okay. So this is the definition of this. But this kind of definition, maybe you just forget about this, what does this mean, because it's too complicated. So, but we can define the restriction What is this? We can define a restriction map. So such that this Z1 is just a restriction of ZPZ. Z2 is just the restriction of WZ. W is just a is that one. Then, so after all this, great, you have, we can define, remember in D we can only define the PQPF, the metabolic one, and in D box delta QP we can define Borel action, but now we can define G action. So that this will be a G module. So this G module is by this, all these complicated things. So if you have 0, 1, 1, 0, Z, it's just Z to Z1. Which one? Okay, sorry. G is always GL to QP. Yeah, because I don't want this to be longer. GQP is a little easier to write. Okay. So, and the second is if A is contained in ZP cross, then this A, so these Borel ones, the diagonal ones, delta A, Z1, delta A, Z2. So now if A is in ZP cross, then A001 Z is A001 Z1, delta A negative 1, 0, 0, 1, Z2. So there's two other, then we are done. So B, if Z prime is 1, is P001 Z, then the restriction of PZP Z prime is P001 Z1, and restriction for ZP Z prime WZ prime. This is delta P, and there is psi Z1, Z2. Okay. So we already have, the only one is now is the unipotent element. So the last is B. If B is contained in PZP, Z prime is 1B01Z. Think, yeah. The other thing we can already find it. Then Z prime is 1B01Z1. PZP WZ prime. And if you know two restrictions, you're gonna get Z prime. Okay, so you either get this, the restriction of this in PZP, and then or this in ZP, you can recover Z prime, or you can in this side you can also recover Z prime. This one is UB PZP Z2. So UB, well, the last thing, UB Okay. It's delta -1 plus b, and then 1, -1, 0, 1. So this is really the lots of computations, and I didn't check yet. Okay, so this is UB. So this is 5. So now, because of this G action, so we really get a G model or G representation. This, okay. So that's quite a lot. So next, so this I think I finished today, and then next tomorrow we will just talk about those theorems, but I will not explain, and I don't know how to exprove it yet. Okay.